Assalamu alaikum, my name is Najaf and my roll number is 21TE06. Today I will be discussing Lab Manual 12 of Digital Signal Processing and the lab title is Infinite Impulse Response Filters. Task number 1. Given the DSP system, this and with the initial conditions, we have to compute the system response yn for 20 samples using MATLAB. Here in this MATLAB code, we have first initialized the time index and the signals. N creates a time index n ranging from 0s to 19. X initializes the input signals with zeros, and Y initializes the output signal with zeros. Then we have set the initial conditions x2 equals to 0 and x3 equals to 1. The set initial conditions are are for x2 and x1 respectively. Then for a computation of x of n, we use a for loop, and for the computation of the output signal, we then again use the for loop that calculates the output signal y of n for n from 3 to 20 using the given difference equation. And then we plot the input and the output signals. For the display of the output signal, we use the display function. And for the zero initial conditions, we reinitialize y to 0 for new computations. And for recomputation of the output signal, we reinitialize with 0 initial conditions for the computation of y of n. Then we plot the y of n with 0 initial condition. So if we run the MATLAB code, we see that the first subplot shows us the input graph. The second subplot shows us the output graph y of n, and the third graph shows us the y of n after recomputing it with 0 initial conditions. Whereas in the command window, we can see the 0 y of n with 0 initial conditions. Task number 2. In task number 2, we have been given a transfer function, and then we have to determine the impulse response, step response, and this is step response y of n if the input is given as this. So here in the MATLAB code, we have defined the numerator coefficients of the transfer function and the denominator coefficients. Then for the computation of the impulse response, we use the function impulse of z to compute the impulse response of the system. To determine the length of the impulse response, we use this capital N. For the computation of step response, we use this function here that computes the step response by taking the cumulative sum of the impulse response. For computing the step response for the given input, here the N shows that the N adjusts the time index to match the length of h, whereas X determines the input signal where u of n is the unit step function. Y of n convolves the input signal with the impulse response to get the system response, keeping the same length as the input. Then we plot the impulse response and the step response. And we display the impulse response, step response, and the system response y using the display function. So when we will run the code, the first subplot shows us the impulse response of the system, whereas the second subplot shows us the step response of the system, and the third subplot shows us the step response of the system y of y system. And whereas in the command window, we can see the impulse response, step response, and the system response here. Task number 3. In task number 3, we have been given the transfer function and we have to plot the poles and zero using the frequency z function. Here in the MATLAB code, we have defined the numerator and denominator coefficients. And for the plotting of the zeros and the poles, we use the figure that creates a new window. And for the z plane plots the poles and zeros for the transfer function defined by the numerator and the denominator. For the plotting of the frequency response, we use the frequency z function. So when we will run the code, we observe first the frequency response, which consists of the magnitude and the phase response. And in the z plane, we can see the plotting of the poles and zeros. Task number 4, we have been given the following transfer functions and we have to sketch the z-plane pole zero plot to determine the stability status of the digital system. Now here in the MATLAB code, we have created a cell array containing the numerator coefficients of each of the transfer function which are stored in the variable num. Same is done for the denominator. Then we iterate over each transfer function and we use a for loop. Then we calculate the poles and zeros of the system using the transfer function 2zpk. Then we simply plot the poles and zero, and for checking of the stability, we use this statement here with an if condition, and it checks if all the poles are inside the unit circle or not. If the magnitudes are less than 1, the plot will show stability. So when we will run the code, in the command window, we can see the stability status for each of the following graph. For the transfer function number 4, the system is stable, as we can see that the poles are inside the unit circle. For transfer function 3, we can see that the system is unstable because the pole is outside the unit circle. For transfer function 2, we can see that the system is unstable because we have one pole outside the unit circle. For the transfer function 1, we can see that the system is unstable as we have the one pole outside the unit circle. Task number 5. In task number 5, we have been given the digital system with the sampling frequency of 8,000 Hertz, and we have to determine the frequency response. So in the MATLAB code, we have defined the sampling frequency. Then we calculate the sampling period using the sampling frequency. For the frequency vector, f is used that creates a frequency vector f ranging from 0 to Nyquist frequency with 1,000 points. For conversion of the frequency from radians to the radians per second, we use this formula here, which is 2 pi into f. For calculating the frequency response, we use this formula, and then we simply plot the magnitude and the phase response. So when we will run the code, we observe the frequency response of the system, where the first subplot contains the magnitude response, and the second subplot shows us the phase response. In task number 6, we have been given the following transfer functions, and we have to plot the poles and zeros on the z-plane, and we have to plot the magnitude and the magnitude, frequency response, and the phase response for each of the transfer function. And we also have to identify the corresponding filter type. Now here in this MATLAB code, we have created a cell array for numerator and denominator, and for labels for the filters, we have labeled the filter as low pass, band pass, and for calculating the uh, length of the, for plotting the z poles and zero, we use the for loop, and for computing the frequency and the phase response, we use the following uh, statement, and then we simply plot the frequency and the phase response, and then we print the filter type in the command window. So when we will run the code, we will observe 8 different filters, 8 different figures. In the command window, we can see the transfer function. It says that the transfer function A is low pass, transfer function B is low pass filter, C is a band pass, and D is also a band pass. Here we can see that we have the pole zero plot for the transfer function A, and it goes on till the transfer function D. Task number 7. For the following feedback filters, determine the locations of the poles and zeros and plot the positions in Z-plane. And we have been given 2 feedback filters. Here we have defined a numerator, the filter coefficients, numerator for numerator 1 and denominator 1, and numerator 2 and denominator 2. Then for computing poles and zero, we use the function the transfer function 2, zeros and poles. For computing poles and zero for the filter 2, we use the same function. And then we simply plot the poles and zeros in the z-plane for filter 1 and plot the zeros and poles in z-plane for filter 2. So when we will run the code, we observe that the pole zero plot for filter number 2 is this. Pole zero plot for filter number 1. In task number 8, we have to determine the poles and zeros for the following given filters. So in the MATLAB code, we have first defined the filter coefficients, and then we convert the transfer function coefficients to these poles and zeros using this function. Then we displayed the poles and zeros for each filter in the command window. So when we will run the code, we observe that the poles and zeros for filter 1 are given as this. pose and zeros for filter 2 and pose and zeros for filter number 3. In task number 9, we have been given the following MATLAB code, and when we observe this MATLAB code here, capital W defines a frequency vector W ranging from 0 to 200 radians per second with a step of 1. Then for computing the frequency response for the filter HA, this HA computes the frequency response of a filter using the frequency S function with a numerator of 10 and a denominator of 1/4. Then for the computation of frequency response for filter HB, we use the function frequency S, whereas the numerator coefficient is 20 and 0, and denominator coefficient is 120 and 100. Then we simply plot the response for the filter. So when we run the code, we observe the absolute filter gain in the first subplot, and in the second subplot, we observe the absolute filter gain for the second filter, HB. In task number 10, we have been given the MATLAB code and we have to perform it in MATLAB. Here we have defined the sampling frequency. Then we design the Butterworth filter using the function butter. Then for the bilinear transformation, we use the function bilinear. Then we compute the frequency response using the frequency Z function. Then we compute the phase response using the unwrap function. And then we simply plot the magnitude and phase response. So when we will run the code, we will observe the magnitude response is plotted in the first subplot and the phase response is plotted in the second subplot. In task number 11, we have to find the frequency response of the design filter in the given MATLAB code. Here we have defined the sampling frequency, the numerator coefficients denoted by B, and the denominator coefficients denoted by A. And then we perform bilinear transformation and we then simply plot the magnitude and phase response. This is the output. Then in task number 12, we have to perform this given MATLAB code in MATLAB. Here, Fs is the sampling frequency, B is the numerator coefficient, A is denominator coefficient, and we convert the analog filter to a digital filter using bilinear transformation using the function bilinear, and then we plot the magnitude and the phase response. And this is the output. In task number 15, we have been given the code and we have to perform it on MATLAB. We have defined the sampling rate, B the numerator coefficients, A the denominator coefficients. Then we use bilinear transformation to convert the analog filter to digital. Then we plot the magnitude and phase response, and this is the MATLAB code. Thank you. That's it from lab number 12. We'll see you in the next video.